So I'm talking about JavaScript as a compilation target. So I want to talk about Dart-to-JavaScript, our compiler. But first, who am I? So I'm a software engineer at Google in Aarhus in Denmark. And my previous projects included Scheme-to-JavaScript compiler. Then in my spare time, I wrote the JavaScript to Scheme compiler. And I worked on V8, virtual machines, and now Dart. So my background is basically Scheme and JavaScript dynamic languages. So what is Dart? It's an unsurprising object-oriented programming language, which for many means it's a boring language, a little bit like Java. But that was kind of our intent. It's a class-based with single inheritance, and the syntax is the same as in Java, JavaScript, and all these C-like languages. And the new thing, at least at that time, was the optional static type system, which recently was seen in TypeScript too. Just to give you a small example, here's the bottles of beer in Dart. Nothing special here. So when we have Dart and we want to deploy it, we have two ways to do it. The first, of course, we have our Dart sources, and then ideally you put it on a Dart virtual machine and run it fast, nice, and everything. And if you still have another browser that doesn't support the Dart VM, which currently even Chrome doesn't, then you have to compile the JavaScript. And then it should run on all modern browsers. And this talk in particular is now about this Dart-to-JavaScript compiler. So there were several goals when we started the JavaScript compiler. So for one, it should run on all modern browsers. And we test on Chrome, Firefox, IE, and Safari. And we have a testing slot for Opera. We just haven't filled it in yet. It's going to happen at some point. And our goal is that the Dart VM is not necessary. So you can program in Dart, and it should still work on browsers that don't have the VM. And of course, it must be efficient and compact. Otherwise, nobody wants to use it. So here's another example of Dart, the standard point example. Nothing special here. We just allocate 2 new points and then take the distance between those two. Note that in this case, I didn't use the type annotation. I just used var, but I could have used typing annotation too. So point or int or double in this case. So here's the compilation to JavaScript for this example. There are 2 things that probably stick out. First is that we put statics on dollar, so it's $dot instead of polluting the global namespace. And the second one that you probably there are actually 3 things. The second one is that there is no new. We just always go through factory constructors, which has a big advantage when you have different constructors for the same class, because we in the background can then use the same JavaScript class and have one hidden map in the virtual machines, which basically means it will run faster. The third thing, is the distance to $1. We encode our arity in the names of the methods. This way, we get exceptions when the arity doesn't work, and we don't need to check the arguments, the length, or anything. We just call, and if it doesn't work, it means that either the arity was not right or the method didn't exist. So this is basically what I just said. Statics on dollar, factory constructors, and functions. Method calls are translated to functions with the arity in its name. So what are the challenges now? One of the big challenges is closures. In fact, when we have JavaScript, as I just said, or as I implied, doesn't check for arity, whereas in Dart it's an error if you don't give the correct number of arguments. And in the previous example, we just encoded the arity in the name of the method, but if you have a closure in the hand, you don't have a name anymore, so you cannot really encode it there. And the second thing is that in Dart we have we allow named or optional arguments, so that's something that would be annoying to encode inside the closure too. And we allow also object instances, so class instances, to be invoked as if they were closures. And there everything breaks down. We cannot use the JavaScript closures as target for Dart closures. The next challenge is operators. JavaScript is very lenient in what it accepts for operator arguments. In fact, it will just try to convert it to numbers or strings and carry on. It will keep on trucking. There's nothing that will basically throw an exception or give an error. And we don't want that. We want to have exceptions when things don't work out. And the second one is that in Dart we have user-defined operators, so we allow to override the plus operator, the minus operator, and so on. And therefore we cannot just compile to the JavaScript plus, because for many objects it wouldn't work. And finally, in a little bit in a similar area, is the array accesses. In JavaScript, array accesses are not checked for out of bounds, or what the key actually is. The links operator in JavaScript works on any object. It accepts everything, starting with integers, doubles, objects, strings, and in some cases it merges them. As you can see, the a of the string 1 is similar to calling a of 1. So all those things are invalid in Dart, and we need to check those. So what are the solutions that we came up with? So for closures, there's actually a pretty easy solution. We compile closures to new classes, and these classes have fields for free variables, and sometimes boxes for variables that are mutated. And then we just put normal methods on them as if they were normal classes, and we treat them internally as classes, basically. And that's working pretty well for two reasons. One is that allocating small objects in JavaScript is very fast, and allocating a closure in JavaScript is more or less the same size as 6 fields. And the second is that every JavaScript engine has heavily optimized method accesses and in their chits, just because every benchmark uses it that heavily. So in the end, you are usually as fast or faster than if you had actual closures. So as an example, here we have a closure, a Dart closure, which starts with the each going to the list index of. So this is a shorthand form for creating a closure in Dart. So the list.map takes a closure that itself takes an each and searches for this element in the list. And this is translated. You have the Dart on the bottom. This is translated into a main $closure class, so the second part, which has one field, the list, so that was the free variable, and it has one method, the call$1, which represents the invocation target if you invoke the closure. And in there, it's just a normal function which takes an argument and does whatever we wanted to do before. Note the compact class representation. So we avoid a lot of boilerplate code by generating code dynamically. This way we shrink a little bit the size of the JavaScript, the resulting JavaScript. So the second problem was the operators. And there, the naive solution would be to just add functions on the prototypes of numbers, arrays, strings, booleans, and so on, and invoke these methods instead of using the JavaScript operators directly. So you could imagine having an add operator on the prototype of number that takes another argument, and only if that argument is actually a number, we return the sum of this plus x. And similarly, for array, the index operator, we would check that the index is an integer, and only if it's then also in the bounds, we return the axis of this. So I have two examples down there. So x plus y would then be compiled to x.add of y, and similarly list the operator of list. The index operator list I would be a method call to the list. So the drawbacks of this solution is that it pollutes the global objects, which is something we really want to avoid, and it also can be very slow, especially if you don't have a strict mode. The reason is that when you do a method call on a number or number booleans and so on, it will box the object before it can do the actual method call. So what we did instead is having static interceptors. So we just have static methods that represent the operators, and they are polymorphic in the sense that for every operator that is for native JavaScript objects, we intercept them in these static functions. So we check if it's a number, and if the other one is a number, we do the operation. If it's something else that supports a plus operator, we would do it in there too. So we just intercept operators in a static function, and then only redirect to the Dart object if if it's not a JavaScript primitive. Similarly, for the index operator, we check if it's a JavaScript array. If it is, we do the JavaScript stuff. And if it's not, we will redirect to the Dart method. So to give you an example of how that looks in the code, this is just a small main that gets the sum of a list. And this is still pretty readable. So every operator is replaced with a call to a static, so $dot. In one case, it's the less than boolified. In the other one, it's the add, and then we have an index. So pretty standard stuff, nothing special. And that works. The only problem is that it's very slow. So we had if you do it this way, you have a slowdown of about a factor of 6 compared to handwritten JavaScript code on V8. And in some cases, it even goes down to 23 times slower than handwritten code. And there are some really obvious improvements. You don't need to use an operator if you actually know the type of the arguments. In this case, you can simulate the inlining of this static function call and avoid the call to the global interceptor. So by tracking the types, and in particular the local types, we can, and doing a little bit of type inference, we can improve massively on that code. Going back to the example that we had before, instead of having all these method calls instead of having all the static calls to the interceptors, we now have only we have none left. In this example, every variable is known, the type is known, so we know that the list is an array. We know that the integer, that the sum is a number. We know that I is an integer. The only thing we actually still have to do is do the checks. So we need to check that we don't have an out of range exception, and we don't have an illegal argument exception in case we have a plus of a number plus something that is not a number. Both can be inlined easily and are pretty fast. So doing just that gives us a performance compared to handwritten JavaScript code of 50%, even a little bit more. And it's a good start to continue from there on. There are two things that are to be noted here. The better your global type inference is, the less static calls you have, so the better you get. And our global type inference algorithm is currently not that good. Something we're going to work on soon. And even if you have a global type inference algorithm that is pretty good, you will still have a lot of calls to interceptors in case when you lose track of the types. And these are doubly expensive because, for one, you have the static interceptor calls, and the second one is you don't know if they have side effects, and therefore they destroy your local optimizations. So the big hammer we have for that is the speculative optimizations, and that's the so the idea is to guess what the type of the variable would be, or instruction, what the type would be based on how it's used. And then we try to optimize for this speculated type. The problem is, of course, we cannot always be right, and therefore we have bailouts when we are wrong. So to give you an idea here, this is the same example as before, the sum of the loop, except that in this case we have no idea what x is. In the previous example, we knew it was a list, it was in the code. In this example, it could be anything. But looking at the code, it would be really great if it was a JavaScript array. So what we do now is we just say, okay, let's check if it's a JavaScript array, and if it is, so if it is not one, we bail out. But if it is one, we can optimize the same way as before, and we have this perfect code that is running nicely and fast. Well, not perfect, but nearly perfect. And then if we are wrong, well, we have a bailout function that does the expensive static interceptor calls and does the necessary stuff to get it right in case there's an operator overloading and it's not a list and all these things. The thing is that if you do that all the time, you blow up your code. So we have some heuristics to when we want to speculate, and it's difficult to see when and how you need to do that. And currently, we just basically say if you're using something from inside a loop, and ideally transitively from inside a loop. So if you call a function that is from inside a loop, you will also optimize that function speculatively. Then we do speculative optimizations. If, however, it's just a function somewhere, we don't care. We keep the interceptors. Ideally, and that's future work, we want to do profile-guided optimizations. So we want to say speculate everything, and then tell us later on what worked and what didn't work. And the things that either always failed out or never were called, we can just leave the calls to the static interceptors and would have nicely reduced code size. So with that, we get another huge bump in performance, and it really, really pays off. So with that, we have about 75% of handwritten code. And to get a little bit on the space-speed trade-off with the speculative optimizations, we have about 15% code increase when we enable the speculative optimizations using the heuristics. And even if we didn't use the heuristics, it would only blow up by a factor by 72%. So for profiling, for instance, it would still be feasible to have all speculatives in and then see which ones are actually effective. Yes, there's another thing we do to reduce the code size. That's tree shaking. The idea here is that we only compile functions that are potentially reachable. So we start with the main, which is the only entry point in Dart. You cannot execute code outside of main. And then we look at yes, colors are better. And then we look at at what is invoked and what classes are instantiated and so on. So in this case, you have two classes that are instantiated, that is point and line, and you have one method call that's the distance to. And then from there on, since it's a method call, you collect all the classes that are there and see, you collect all the methods that are possible. In this case, let's assume point and line have a distance to method on them. And you continue recursively enumerating the functions that are potentially reachable. In this case, it could be, for instance, square root and a cross product and point and so on. As you can see in this example, you might end up compiling too much. Nothing in the code that is shown, at least, tells you that you call line.distance off. The only one that is there is a point.distance to. Sorry, distance to. But it's still a good. It still reduces the code size by a lot. And the more typing information you have, the better it gets. So in another diagram saying the same thing, what we do is we start by parsing the whole code, but diet parsing, which means that we don't actually create the AST for everything. We just get the structures, what are the classes, what are the methods, and so on. Then we resolve using the tree shaking algorithm, and there we actually build the ASTs. And then at the end, we do another tree shaking like compilation process where we compile only the methods that are actually called, knowing that the compilation might do that code elimination and so on, and that's why the compiled code could be less than the resolved code. Since we are talking about compilation, I'm now going to the static single assignment form. So this is how we compile. We start with a Dart syntax tree, then go through a builder that builds our SSA graph, do some optimizations on that, a lot of optimizations on that, and then go to the code generator, which code generator, which will produce a JavaScript syntax tree, which will then emit to get the final code. So the single static assignment form is commonly used in tons of compilers, and we use it for analysis and optimizations too. In particular, we have the local type inference, which uses the SSA form. Function inlining is, well, it's kind of on the builder level, but partially on the SSA. Global value numbering, and I'm going to I have a slide on that one. Also the loop invariant code motion. I have a slide just afterwards. And finally, range propagation, where we just keep track of the value ranges a variable can have. Note that SSA is actually pretty annoying in some respect when you compile to JavaScript, because going out of the SSA form back to JavaScript is not always trivial, because there's no goto in JavaScript. It can be tricky to actually compile back to nice JavaScript, and we spend a lot of time on that. So the global value numbering I mentioned, it basically just tries to avoid recomputing stuff if you already have computed it. So in this case, compiler.generated, assuming that we know that compiler.generated is not a getter, we can avoid accessing it twice, just doing it once before the if, and therefore avoiding a little bit of code and of execution. In the same way, in loop invariant code motion, if we can show that we can hoist a computation out of a loop, well, let's just do that. It's as simple as that. Funny enough, most of those are not that important for us because the chits then do that already. So only in a few cases where we have a little bit better information than the chits can we do more than they do. But it still gave us some percentages. Here's now the sum example from before with the optimizations applied. There are only two changes from before. For one, we have now the list.length, which is hoisted out of the loop. So that's the var t1. Then the second one is that the range propagation made sure that we don't need to check for the out of bounds exception. Other than that, no change. So what's the status of the Dart-to-JavaScript compiler? With respect to code size, we have improved a lot since our first release. So everybody still remembers the megabyte hello world. That's not there anymore. And usually now, if you have an app that produces a lot of JavaScript code, it's because you use libraries. So it's not that we cannot make our code better, and we can definitely make it better. But in many cases now, it's not stupid errors anymore or stupid code generation as there was before. And we are working on a minifier already. So we have a Dart-to-Dart minifier, and we have a minification for JavaScript where we remove the white space at least. And we are working on minifying the local variables names and everything too. With respect to performance, this is a screenshot of our internal tracker. The important one is probably the last number on the bottom and the right, which is the Dart-to-JavaScript performance with, compared to V8 to handwritten V8 code. So the geometric mean says that we are now at 78% of the handwritten code, at least for the benchmarks we have here. And we would think we can still improve on that. So it's not yet done. And then some benchmarks we are in the fastest, some. So as conclusion, speculative optimizations, I think that's the big takeaway from this talk. It's crucial to get a real good performance if you have dynamic code. And we are now more than 75% speed of handwritten JavaScript code, so it's a good time to give Dart another try if you have done it before, and a try if you haven't. And with that, I thank you, and I will take questions.
Do you have any questions out there? Anyone? Come right up.
The loop invariant code motion, where and how do you have more information than the JIT? Do you have a concrete case where you know more than the JIT and can do better?
Out of the top of my head, I don't, but I'm pretty sure there are some cases where we compile something into a method call just because it's simpler or because we don't want to inline it, and we still know that this method call doesn't have any side effect. And if the VM doesn't inline it, it will not see the same thing. And also, doing this might help us optimize ourselves, code ourselves. So if we can basically bail out earlier, that's the biggest thing. If we can move it out of the loop and then have a bailout that is not inside the loop but outside the loop, we are much faster.
So you briefly mentioned, hello.
Yeah.
Hi. You briefly mentioned getters, and of course in ES6 we're going to be getting proxies, which all make this, I imagine, a lot harder. Do you have a strategy for dealing with that, or are VMs and compiled to JS languages and optimizations in general just kind of screwed once proxies roll around and once getters start being more prevalent?
Well, for us it shouldn't matter because we compile to JavaScript, so as long as the current set doesn't change, the current language doesn't change, we should be fine. On the other hand, it could help us. So for instance, getters and setters, when we started Dart-to-JavaScript, it was just a no-go. We couldn't compile Dart getters and setters to JavaScript getters and setters because they were horrendously slow. Whereas now, I think there are some benchmarks appearing that actually use it. So the chits start to optimize them. So everything that comes into JavaScript is just helping us.
Actually, I have two questions. One, what if you have a jQuery on your page? Like $sign is kind of very popular. And another, do you have a tail call recursion?
Sorry,
Do you have a tail call optimization in Dart or not? And if you do, what do you compile to?
Yeah. So second question is easy. No, we don't have it. And the first question is, at the moment, there's a conflict, but we can easily change dollar to something else. There's no, that's really easy.
So you mentioned minification at the end, that you might add that in. Are there specific pieces of information you have in Dart that you think could help with minification beyond just what you can get from a post-hoc minifier?
So for us, minification is much easier than for JavaScript, and I hope I'm responding to your question, because we don't have dynamic code generation or even accessing through strings, as long as you, of course, don't use mirrors, which is reflection. So as long as you don't use reflection, we can just minify every method to the corresponding minified name, and we know that it will not be a problem because nobody can use a string to access it, or nobody can generate new code to do that. So from that, it seems pretty just having a map from to for methods, statics, and everything should do the job.
Tree shaking, if I understood it correctly, wouldn't work with library code. But would it work if you included all your, or if you recompiled your library code together with the application? That's
what we do. When you compile from Dart to JavaScript, we take the whole code, we put it into one file, and we tree shake everything away. And we have the Dart compiler to do basically the same thing when you deploy on Dart.
Any other questions? All right, cool. Thank you, Florian, very much.
Thanks.